Last video, a boat was driven forward by the water it caught. Mass flowed in carrying momentum. Now the same idea runs in reverse. A rocket in empty space has nothing to push against. No ground, no air, no water. Yet it accelerates. The only thing a rocket has is its own fuel, so it throws that fuel backward, hard, and the recoil drives it forward. This video we derive the equation governing that trait, the rocket equation, and find inside it exactly where thrust comes from. Here is the setup. At time t, a rocket moves with velocity v sub r of t, measured in a fixed inertial frame. Call it the ground frame. Its engine burns fuel continuously and ejects the exhaust backward with velocity u. And here is the most important sentence of the derivation. U is measured relative to the rocket, not the ground. Exhaust speed is a property of the engine, the chemistry of the burn, the shape of the nozzle. So a given engine ejects fuel at the same U, whether the rocket is crawling or streaking. Right along in the rocket's instantaneous rest frame, and the exhaust always leaves at U, straight backward. Watch from the ground, and the exhaust velocity is the vector sum, U plus V sub R. Confuse those two frames, and every sign in the rocket business goes wrong. The fourth story is Newton's third law. To hurl fuel backward, the rocket must push on it. The fuel pushes back on the rocket, equal in magnitude, opposite in direction, forward. And because fuel is leaving, the rocket's mass, m sub r of t, changes at the rate dm sub r dt, a negative number. Our goal is one differential equation connecting the acceleration, the mass rate, the exhaust velocity, and whatever external force acts. That equation is the rocket equation. The procedure is the one this whole lecture runs on. Apply the momentum principle to a system whose mass never changes over the interval from t to t plus delta t, with delta t small. The limit comes at the end. Choose the system to be the mass of the rocket at time t. Write it m sub c equals m sub r of t, and that splits into two pieces. M sub rd, the dry mass, structure, engine, payload, plus m sub f of t, the fuel still aboard at time t. During the interval, the engine ejects a small batch of fuel of mass delta m sub f backward at u relative to the rocket. As delta t goes to 0, the batch delta m sub f goes to 0 with it. The rule from 3 videos back applies word for word. The system is the same collection of matter at both snapshots wherever that matter ends up. At time t plus delta t, that matter sits in two places. The rocket now has mass m sub r of t plus delta t, which we write as m sub r of t plus delta m sub r. And since the rocket is losing mass, delta m sub r is negative. The ejected batch, delta m sub f, flies free behind it. Add the pieces, the system's mass at t plus delta t is m sub r of t plus delta m sub r plus delta m sub f, but the system's mass is constant. It still equals m sub r of t cancel. And the delta m sub r equals minus delta m sub f. The rocket's loss is exactly the exhaust's gain. Now the two momentum diagrams, both drawn in the fixed frame. At time t, the system is one body, the rocket, mass m sub r of t, moving at v sub r of t. The batch included still aboard and riding along at that same speed. The system momentum is m sub r of t times v sub r of t. At time t plus delta t, the same matter is two bodies. The rocket of mass m sub r of t plus delta m sub r now moves at v sub r of t plus delta t. The ejected batch takes more care. This is where the frame distinction earns its keep. The batch leaves at u relative to the rocket, and the rocket moves at v sub r of t plus delta t relative to the ground. So relative to the ground, the batch moves at the vector sum, u plus v sub r of t plus delta t. One only simplification sits underneath this. In reality, the batch is ejected gradually across the interval, its velocity changing as it goes. We pretend the whole batch leaves at the final instant, t plus delta t. And as delta t goes to 0, that pretense becomes exact. One more subtlety, because the picture can mislead. The diagram draws the exhaust moving backwards through space, and it does, when the exhaust speed u is larger than the rocket's speed. But a fast rocket can outrun its own exhaust, then the ejected fuel still drifts forward in the ground frame, just slower than the rocket that dropped it. Either way, the vector sum handles it. The algebra never asks which way the exhaust actually drifts. Now assemble the momentum at t plus delta t. The rocket's piece, m sub r of t plus delta t, times v sub r of t plus delta t, plus the batch's piece, delta m sub f, times the quantity u plus v sub r of t plus delta t. Two substitutions clean this up. First, the rocket's new mass. M sub r of t plus delta t is m sub r of t plus delta m sub r. Second, the mass bookkeeping. Delta m sub f equals minus delta m sub r. The momentum at t plus delta t becomes the quantity m sub r of t plus delta m sub r times v sub r of t plus delta t minus delta m sub r times the quantity u plus v sub r of t plus delta t. Expand and watch the middle terms, plus delta m sub r times v sub r of t plus delta t from the rocket, minus delta m sub r times v sub r of t plus delta t from the batch. They cancel exactly. Nothing second order left to throw away this time. What survives is compact. M sub r of t times v sub r of t plus delta t minus delta m sub r times u. Now the momentum principle. The external force equals the limit as delta t goes to 0 of the change in system momentum over delta t. Subtract the momentum at time t m sub r of t times v sub r of t and split the quotient into two limits. The first, m sub r of t, times the limit of v sub r of t plus delta t minus v sub r of t over delta t. That limit is the derivative dv sub r dt. The second, the limit of delta m sub r over delta t times u, that is dm sub r dt times u. So f sub x equals m sub r of t times dv sub r dt minus dm sub r dt times u. This is the rocket equation. Look at what the careful bookkeeping brought. The mass rate multiplies u, the exhaust velocity relative to the rocket. A lazy product rule on the rocket's momentum alone would have put the rocket's own velocity there instead, an answer that would change from one inertial frame to another, which no real force can do. Now put the equation in components because that is where the signs teach. Let the rocket move along the positive x direction. With external force F sub x along x, the exhaust goes backward, so the exhaust velocity as a vector is minus u in the x direction, the symbol u now standing for the exhaust speed, a positive number. The rocket's velocity component is v sub rx. Substitute into the rocket equation and read off the x component. F sub x to s equals m sub r of t times dv sub rx dt plus dm sub r dt times u. Watch the sign flip, the equation's minus sign times the exhaust's minus u gives plus dm sub r dt times u. Next, name the burn rate. Take the ejected batch delta m sub f, divide by delta t, and take the limit. That is dm sub f dt, the rate at which spent exhaust accumulates behind the rocket, a positive number. Note the switch. M sub f now counts exhaust thrown away, not fuel still aboard. Every kilogram the exhaust stream gains is a kilogram the rocket loses, so dm sub r dt equals minus dm sub f dt, the same rate, opposite signs. Finally, move the mass rate term across to sit beside the external force. F sub xtx minus dm sub r dt times u equals m sub r of t times dv sub rx dt. The right side is mass times acceleration. The left side now holds two pushes, and only one of them is a real external force. The second term on the left has a name. The thrust, F sub thrust x equals minus dm sub r dt times u, and using the burn rate, that is dm sub f dt times u burn rate times exhaust speed. Check its direction, sign by sign. The burn rate dm sub f dt is positive. The engine is burning. The exhaust speed u is positive, so the thrust is positive. It points forward along the motion exactly opposite to the direction the fuel is thrown. Check its size. Double the burn rate or double the exhaust speed, and the thrust doubles. With the thrust named, the rocket equation reads like Newton's second law, m sub r of t times dv sub rx dt equals F sub x plus L sub thrust x. Mass times acceleration equals external force plus thrust. But keep the bookkeeping honest. The thrust arrived on the force side by rearrangement. Nothing new pushed on the rocket. That term is the momentum the rocket keeps for itself by throwing mass away. Step back and say what the thrust is. It sits in the equation like a force, and it is measured in newtons like a force, but nothing in the environment applies it. No ground, no air, no launch pad. It is recoil, Newton's third law running continuously. Every second, the rocket hurls a little mass backward at speed u, and the reaction to each hurl pushes the rocket forward. That settles the old riddle of how a rocket accelerates in empty space with nothing to push against. It carries the thing it pushes against, its own fuel. And the deciding term from 2 videos back, mass rate times relative velocity, has kept every promise. For the leaking sand, the sand left at the car's own velocity, relative velocity 0, term dead, no recoil. For the rocket, the fuel leaves at the full exhaust velocity, engineered to be enormous. The term is the whole story. What we hold is a differential equation. Mass times acceleration equals external force plus thrust, with the mass itself draining as the burn goes on. Next video we integrate it in free space, then in stages, then against gravity, and find out how much velocity a tank of fuel actually buys. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.